Thank you for your introduction. I'm Yuki Kuta from Tokyo Metropolitan University. And today I'd like to introduce about the attention-based contextual multi graph conversion networks for short-term population prediction. So basically our goal, our research goal is to try to predict the future population through stays in urban areas in 1 hour later from currently, based on the past observed data. So we construct the model to predict the future population figure. And predicting short-term future population can be beneficial for various applications, such as the avoidance of congestion and the operation of out-of-home advertising. And however, the count data observed in urban areas like population data is known to have a complex spatial and temporal dependencies. So the basic idea of the handling this data is to partition observed region into grid structure. And by using grid structure, it's possible to consider both spatial correlations and temporal correlations simultaneously. And basically, there's two popular models to predict the two popular deep learning based model to predict these population spatial and temporal dependencies, which are LSTM for the temporal dependencies and convolutional neural networks for the spatial dependencies. However, there's a couple limitation in the convolutional neural networks. First, CNN uses a rectangle filter to consider the information. So we can interrupt this operation, as in the urban areas, it is considering spatial dependencies based on the Euclidean distance. So by using these rectangle filters, it is impossible to consider the unique spatial correlations, such as the layout proximity and POI distributions. So to handle this problem, we propose a following framework. First, we convert the grid structure into a graph by utilizing urban environment information, such as the POI distribution and transportation networks. And after that, we capture spatial correlations by using graph convolution networks. And finally, we constructing multiple graphs and fusing outputs of these conversion layers to consider spatial correlations from the multiple views. And this paper, in our research, we construct the three graphs, each distance graph, POI graph, and the transportation graph. And the importance of each of these three views for the future prediction might be different in each region. Besides, it will be affected by contextual situations such as the weather conditions or holiday information. So to solve these problems, we use the contextual-based attention module, which basic idea was proposed in taxi demand prediction paper. So I visualized the basic idea of our research. So the first model uses multiple views to try to make the prediction. And by considering the contextual information, such as the weather and time of the information, the model assigned the different weights for each region of these three aspects by considering this information. And the another advantage of using the attention module is we can visually confirm how the model leverages the urban environment information. So in the later part, I will show the attention weight calculated by this model. So the contribution of our work has two folds. First one is we propose a model that can capture multiple spatial correlations. And the second part is we confirm the importance of each graph to the population prediction by visualizing the attention weights. And we named our proposed Nobel methods attention-based contextual multi-view graph conversion networks, and we call this ACM bridge GCMs. So in this figure, I showed the architecture of our proposed ACM bridge GCMs. So basically, first it will be capture spatial and temporal correlation for multiple aspects, which mean distance, POI, and transportation. And we use the GCNs to capture spatial dependencies. And after that, we use the GRU to capture the temporal dependencies. And since there's a three blocks in parallel, so there's a three output values in here. So after that, we fuse its multiple outputs via attention module, as I already mentioned, and which consider contextual situations such as the weather and POI distribution. And finally, the model make the predict for the future population. So I'd like to explain about each step more deeply. So first part is the construction of graphics. And as I already mentioned, we construct three different graphs. And in this paper, we assume that the graph are undirected. So first part is the distance graph, and we define the adjacency matrix of distance graph by using a thresholded Gaussian kernel. So this VN means the each grid used in this paper, and the distance, this means the Euclidean distance between two grids. And by calculating this adjacency matrix like this, we can define the distance graph by this formula, and capital V means the set of all grids of the target region. And next is the POI graph, and we first obtain POI data from a website and in the shapefile format, and classified in the 9 categories. And we calculate POI distribution vector of each region, denoted as TN, by using a TF-IDF metrics. And after calculating each vector, we use the cosine similarity between two vectors to define the POI similarity. And we define the POI graph as this formula. The last part is a transportation graph, and basically we consider railroad and the highway as the transportation networks. And the vector GM is the transportation's distribution vector of grid GM. And we assign 1 to each entry of the vector when the grid overlaps with the corresponding train stations or highway roads. And after that, we simply take the inner product to calculate the adjacency matrix. So I visualize the procedure of this calculation. So please imagine that there's 2 regions, and each vector has the binary elements which denote that as the corresponding transportation network is overlapped with the region. And by defining this vector, just calculate the inner product, and we can obtain the strength of the connectivity of different region. So after creating the graph, we use the cabinet to capture the spatial dependencies, and the cabinet is known to the it's a model computational efficiency GCN to capture the correlations. And after calculating spatial dependency by using cabinet, we use the GRU to consider the temporal dependencies. And as for the contextual information, we consider 3 aspects. First one is the weather conditions, and second is the time of day, and the last is the holiday information. And basically, we embed contextual information at this time interval by using embedding layer of the neural network and obtain a vector of the contextual information. And the last part is a contextual-based attention module, which used in the ACM-based GCMs. And first, the model concatenate three output values, which mean these three colored vectors calculated by the different graph, and the contextual vector and the PY distribution of the grid VM. And after that, it calculates the attention weights by using one fully connected layer and use the softmax layer and calculate weight. And after that, it will be fuses multiple outputs values by using this calculate weights, and finally make the final prediction. So the advantage of this module is it is possible to dynamically change the weights assigned to each spatial aspect for each region by considering contextual situations. So that is the basic idea of our proposed model. So as for the next part, I'd like to talk about the dataset description. We use the mobile data called mobile spatial statistics, which is population count data collected from mobile devices, location information. And as for the spatial granularity, it has the 500 net size grids. And as for the temporal aspect, it's recorded once every hour. And the data set is looks like this. And in this paper, we accept the people who are visiting municipality different from where they live, and define as the prediction target. And as for the experiment setting, we set the train data, validation data, test data as the period written here. And as for the investigated area, we set 32 times 40 size grids from the center of Tokyo. And as for the metrics, we use the mean absolute error, root mean square error, and weight average percentage error. And basically, we iterate training and prediction 10 times for each model and evaluate performance with the average of them. And I listed the baseline model used in the experiment here. And I just want to explain about this model called MVGCN. It has the same architecture as our proposed ACMVGCN, but it's eliminate the attention module. So it just make the final prediction by using just taking the average of three predicted values. So there's a kind of the aggregation study, just eliminate the attention module. And I show the performance comparison among the different models, and we can we can see two findings from this table. First, the ACMB GCNs, our proposed model, shows the best performance in all metrics. And the another finding is every GCNs which do not use the attention module performs worse than the ACMP GCNs. So these results demonstrate that the effectiveness of the proposed method, and also the effectiveness of the fusing multiple outputs by using attention module. And this table shows the performance comparison among model uses different graphs. And I listed the graph used in the model in here. And from this table, we can see MVTNs, which uses all graphs achieve the best performance. So this result demonstrates the effectiveness of the conserving spatial correlations of urban areas from multiple views. And this figure shows the attention weights calculated by the model, and I visualized those weights in this map. And the red color shows the weights assigned to the PY graph, and green shows the weight assigned to the transportation, and blue shows the weight assigned to the distance graph. And also I showed the transportation structure with this railroad and the highway in this map. And from this map, we can see kind of the weights assigned to the PUI graph, which mean the red color figures. show high value in the major shopping and entertainment hubs of Tokyo, which means there is a Tokyo station here, and Ikebukuro station and Shinjuku station, and Shibuya station is straightened here. And I hope you are familiar with this station, but it is very popular in Japan. And also another findings is the weights of transportation graph, which means the colored in green, mostly overlap with the rate of distribution. So from these results, we can understand that proposed model successfully runs a variable way to leverage urban environment information. So the last part is I visualize the attention weights in various contextual situations. So first setting is a business day with sunny weather. And first we can, from this transition of the attention weight, we can see the weights assigned to the POI graph and transportation graph become larger in the morning to the evening. It become larger from the 9 a.m. So it's compared to the midnight, we can see these weights are relatively low. So from this result, we can see the proposed model change the weights values based on the time of the information. And we can understand this behavior is very reasonable, since by considering operation time of the POI facilities and transportation. And the second situation is a business day with rainy weather. We observed two rainy times in this figure. However, there's no remarkable difference between weights of the sunny weather. So we can understand the model paid little attention to the weather conditions when calculating attention weights. We can interpret this is because of the seasonality reason. Usually there are only few precipitation observed in Tokyo from January to March. So I think we understand this is because of the relatively low effect of the weather condition. And the final situation is holiday with sunny weather. And from this figure, we can understand overall the weights assigned to the POI graph, which means red color, and the transportation graph, which means green color, is relatively low compared to the weights observed in the business day. Because we can interpret this is because the effect of the number of commuters, since there is low commuters in the holidays, the transportation POI importance is become relatively lower than the business day. So overall, this observation, we can understand the proposed model success in learn how to utilize urban environment information efficiently. So as for the conclusion, first to summarize our work, we propose a model which essentially captures spatial dependencies from multiple aspects by considering contextual situations. And as for the contribution, first we propose a model which success to outperform the baseline models. And another contribution is we confirm how the urban contextual information contributes to the population prediction by visualizing the attention weights. That's all for our presentation, and thank you for your attention.
Great. Thanks, Yuki, for this great work. And is there any questions from audience? Yeah, we have one question. So this model is interesting, and will conduct experiments about the multi-step prediction. Why it is only used for short-term prediction?
Okay, thank you for your question. Basically, I haven't tried the multi-step prediction, not yet. And there is no reason that this model needs to predict only for short-term population. But basically, I suppose we need to use like a seek-to-seek architecture to predict the multi-step future population. And it is because relatively complex. So this is just like the first step of this population prediction. And I also considering to expand this model for the multi-step prediction, but I haven't tried it yet. So this is kind of the future work.
Okay, cool, great. So is there any other questions? Yeah, it's about the attention mechanism. It seems to be a global attention algorithm. If you try some other approaches to calculate the importance scores, such as the multi-head attention.
Thank you for your question. Actually, I haven't tried it, not yet. So yeah, as you mentioned, it's just calculating that global attention weights. And yes, it might be useful to calculate the kind of multi-head attention from different aspects, but yes, I haven't tried it yet.
Okay, cool. And I also have a simple question. Maybe I didn't catch up on you. So, it's in your architecture, the framework one.
Mhm.
I remember that you have a POI graph and also have a POI vector. So, what's the difference between these two? Maybe I didn't catch up this one. So, can you
Thank you for
give a
your
little bit explanation about this?
question. Okay, basically, the POI vector is same as the used in this graph construction of the graph. So we are using the same vector, but when constructing a graph, it's calculating a cosine similarity between these two vectors, and you use this graph to capture the spatial dependencies. And for the attention calculation, it just use the vector of the POI, not calculating something like a cosine similarity. It just concatenate this row vector and calculate the attention weights. This vector used in the model is same.
Okay, so do you do any oblation study like remove the POI vector to see what the performance of your model, the right part, not the POI graph?
Basically, I just eliminate the attention module you think here. So I think it will be like this model, which called MVGCN. So
Okay.
this model do not use the attention module, so it do not consider the contextual vector in this model, and we can see our proposals outperform this baseline.
Okay, cool, cool,